This is a famous mathematical riddle, and it goes something like this. A bird and train depart at the same time. The train travels at 50 miles per hour, and the bird travels much faster at 240 miles per hour. 100 miles up the track, a second train also departs at the same speed as the first train. Unfortunately, it's in the opposite direction. Once the bird encounters the second train, it turns around and flies back to the first train. But after encountering the first train again, it turns around and heads back towards the second train. It continues this back and forth motion between the two oncoming trains until So the question is, what is the total distance the bird traveled before the trains collided? There are at least two ways to get the right answer, but one method is much faster than the other. We'll cover them both, but in the meantime, let me know how you would approach this problem in the comments below. And stay tuned for this episode of Dr. John. Before we dive into the solution of this problem, here's a little backstory. A variation of this bird train problem was famously posed by Max Born to his closest friends and colleagues. And in case you're not familiar with Max Born, his closest friends and colleagues weren't exactly lightweights. Surprisingly, none of them really figured out the solution very quickly, so don't feel too bad. Max Born himself was a Nobel Prize-winning physicist for his contributions to quantum mechanics, most notably for drawing the mathematical connection between a particle's wave function and its probability density, one of the cornerstones of quantum mechanics. He also joined Werner Heisenberg in developing the matrix mechanics representation of quantum mechanics. And fun fact, his granddaughter is the 4-time Grammy winner, Olivia Newton-John. Impressive family. So Max Born is at a pretty highbrow cocktail party and runs into John von Neumann. And while John von Neumann never won a Nobel Prize, he's not exactly a lightweight either. Among his achievements include designing the implosion-type nuclear bomb during the Manhattan Project, generalizing quantum mechanical states to points in an infinitely dimensional Hilbert space, formulating a mathematical framework of game theory, along with many, many others. He also worked on improving the first ENIAC computer after his experience with the slow computing machines used during the Manhattan Project. Through his efforts, he developed the first single-processor stored program architecture, which became the basis for almost all computer design, and subsequently is often referred to as a von Neumann architecture. So back at this party, Max knows von Neumann is a bit of a polymath, and is curious if he'll be able to tackle this deceptively simple mechanics problem. So he explains the two trains approaching each other with the bird flying back and forth, and asks von Neumann to find the total distance the bird travels. But by the time Max Born finished asking the question, von Neumann instantly responded with the correct answer. Astonished, Born replied, "You were the first one of my scientist friends who solved the solution at once. You must have known the trick." Puzzled, von Neumann responded, "I don't understand. It's a simple infinite geometrical series." Simple is a relative term, I suppose. To see what von Neumann was talking about, we're going to tackle the steps of this classic problem. We'll also investigate that trick Max Born was talking about, which, if you're as smart as von Neumann, you don't really need it. But before we get too far, make sure to subscribe to my channel and hit that like button. It helps my channel grow, and I really appreciate your support. Okay, so let's set this problem up formally. Two trains are on the same track and separated by 100 miles. So let's take note of this distance and call it D. Each train travels at the same constant speed of 50 miles per hour, which we can label as v sub t1 and v sub t2. The bird overhead travels much faster than the two trains, at a speed of 240 miles per hour. Fast bird, maybe a peregrine falcon. So let's label this bird's speed as v sub f. Let's box these and save for reference later. Now, we want to find the total distance the bird travels, which we can label as x sub f. This essentially can be broken into a series of distances. This includes x1, or the distance the bird travels before meeting the second train, plus x2, being the distance of the bird's return to that first train, plus x3, the distance the bird travels back to the second train. You get the idea. These back and forth distances continue until the trains collide. Now, since we weren't given any of the x sub n's in the problem statement, we need to rewrite these terms given the parameters of our problem. These distances correspond to the bird's travel distances, so we can rewrite each term as the product of the bird's speed, v sub f, multiplied by the time taken to complete that particular leg of the journey. For instance, x1 can be rewritten as v sub f times t1, and so on. After making these substitutions, we can factor out the v sub f from each term, and then we can also rewrite our summation taken over x sub n as the product of v sub f and t sub n. We don't have explicit expressions for these t sub n terms either, but time is at least a shared variable between the bird and each train. Algebraically, this will make it possible to write linearly independent expressions, and then solve in terms of our known given parameters. I'll show you exactly what I mean by this, but essentially, we need to find expressions for each time term in the summation, and then look for patterns, and then go from there. Let's begin with t1, and let's backtrack to that leg of the journey. This is the time when the bird has met the second train and traveled over a distance of x1. So we can write our first expression as x1 equals v sub f times t1. Now, during that same time t1, the second train has also moved a particular distance. And comparing with the train's original position, the second train has traveled through a distance of d minus x1. Using the train's speed to relate this distance with t1, we can now write a second expression, namely d minus x1 equals v sub t times t1, where we've dropped a numerical subscript on the train's speed, since it's the same for both trains. This brings us two equations with two unknowns, x1 and t1. We can add these expressions together and the x1 terms cancel out. This leaves a nice single variable expression which we can solve for t1 in terms of our initial given parameters. Let's box this answer for now and continue looking at the other time terms such as t2 and t3 in a similar manner. And before we proceed, let's take note of the new distance between the two trains. Each train has traveled a distance of d minus x1. So the new distance between the two trains is equal to the original distance d minus 2 times d minus x1. Now, let's try and find an expression for t2. During this time, the bird travels back to the first train over the distance x2. So in a similar manner as before, we can write our first expression as x2 equals v sub f times t2. Now, for the second expression, we can again focus on the train's travel distance and speed. This is simply equal to the train separation distance we just found minus x2. Tying this into equation 4, we can set this equal to the train's velocity, v sub t, times t2. Now, we can add equation 3 and equation 4 together and hopefully eliminate some variables like before. So, after summing, x2 is eliminated, but the sum still contains two variables, x1 and t2. But remember, x1 just equals v sub f times t1, which we boxed earlier. So let's make these substitutions. The left-hand side is looking a little complicated, so we can clean this up by factoring out a d from each term, combining the mixed fractions, and then combining like terms. So now this expression can easily be solved for t2, and we can also box this answer for now. In order to make real progress on this problem, we need to find a general expression for t sub n. Comparing t1 and t2, there are some similarities here, but it may be a bit bold to determine a pattern based on only 2 data points. So to be sure, let's repeat this process one more time and find an expression for t3. The logic for finding t3 remains the same as before, but the expressions will begin to look a little verbose. Most of the expressions can be simplified, but I've kept them in long form to help better internalize the iterative nature of this problem. So hang on, and things will clear up soon. As we did previously, before we find t3, let's find the new distance between the trains. The previous distance between the trains was d minus 2 times d minus x1. By the end of time t2, each train traveled this distance minus x2. So the new distance of separation between the trains is the previous distance minus 2 times the distance each train traveled during time t2. And fortunately, this long expression simplifies nicely into d minus 2 times x1 plus 2 times x2. Now, applying the same logic, let's find an expression for t3. During time t3, the bird travels back to the second train over a distance of x3. So we can set x3 equal to v sub f times t3. Now, in the same amount of time, t3, the second train travels a particular distance, which is equal to its initial distance of separation minus x3. Tying this together algebraically in equation 6, we can set this new travel distance equal to v sub t times t3. As before, we can eliminate variables by adding equations 5 and 6 together. In addition to t3, the resulting expression now contains x1 and x2. But again, since we know the bird's speed, v sub f, and we found the times t1 and t2 from before, we can eliminate x1 and x2 with the appropriate substitutions. Now, the substitutions for t1 and t2 make the expression a bit lengthy, so we'll temporarily hide the right side of the equation and bring it back after some of the dust settles. So for the left-hand side, we can begin by factoring out the common d factor in each term's numerator. We can then combine each fraction using the lowest common denominator of v sub f plus v sub t squared. Now, in this lengthy numerator, the only terms that survive are the first squared term and the mixed v sub f, v sub t cross terms. Finally, this factors nicely as v sub f minus v sub t squared. Now, bringing back the right-hand side of the equation, we can easily solve for t3. And we can box this answer. At this point, you may begin to see a pattern emerging, and we can try to form a general expression for t sub n. Oh wait! Sheesh. Well, from this point onward, we shouldn't need the diagram anymore anyway, so good luck out there. To find t sub n, we can take a look at our expressions for t1, t2, and t3, and look for some trends. First, you might notice that the quantity in each term's denominator is raised to a power that matches the index of its corresponding time term, t. For instance, for t1, v sub f plus v sub t is raised to the first power. For t2, this quantity is raised to the second power, and so on. So we can infer that t sub n must be inversely proportional to the quantity v sub f plus v sub t raised to the nth power. Next, we can easily see each expression for t carries a factor of d in the numerator, so we can carry this over to t sub n as well. Now, what about the difference term in the numerator? That is, v sub f minus v sub t. The pattern for this one is a bit more difficult to see, as it doesn't even appear in t1. We can make this a little clearer by including this difference factor in the numerator of t1, and then raising it to the 0th power, a completely equivalent expression. Now, the pattern is a bit more obvious. Each expression for t now contains this difference term raised to the power of its respective index, minus 1. So in t1, this term is raised to the 0th power. For t2, this term is raised to the first power, etc. So for t sub n, we can write this difference term as being raised to the n minus 1 power. Now our expression for t sub n includes all the factors from t1, t2, and t3. So we can flip the proportionality sign to an equality sign and box this expression. We're getting really close now, and we're ready to tackle this infinite sum. So after substituting our derived expression in for t sub n, we can make a few adjustments. We basically want to write the sum in a recognizable form that ideally will converge to some finite value. We can start by factoring out d from the summation since it's not attached to an index. Next, notice the mismatched powers of n minus 1 and n between the numerator and denominator. To force these to match, we can take out a factor of v sub f plus v sub t from the denominator. This lowers the indexed power term of the denominator to n minus 1, and we can move the non-indexed term in front of the summation. Now, the powers match, but having all powers raised to the n minus 1 is a bit verbose, especially since the sum begins at n equals 1. This can be improved by lowering the index of the summation to n equals 0, which effectively raises each indexed term of the summation by plus 1. This is a common technique for working with infinite sums, and can really come in handy when trying to match an infinite sum with a recognizable form. Now, we can clean this up by carrying the nth power outside of the fraction. At this point, you may recognize the summation as having a similar form to the geometric series, which is what von Neumann recognized right away. The geometric series is a special infinite series consisting of a constant, usually labeled by r, raised to the nth power. It's particularly useful since the geometric series not only converges, but converges to a very simple closed form expression, namely 1 over 1 minus r. However, it only converges if, and only if, the absolute value of r is less than 1. Otherwise, it diverges to infinity. So comparing with our series, we can let r equal our fraction contained within the summation. Since all of our velocities are constant, this must also be a constant. But we must ensure the absolute value of this fraction is less than 1, or else we're out of luck. So substituting 240 miles per hour in for v sub f and 50 miles per hour in for v sub t, we find this fraction equals 19/29, which fortunately is less than 1. This is great! This means we can substitute the closed form solution of the geometric series in for our infinite sum and use 19/29 for r. Now, this mixed fraction becomes 29/10, and we can substitute our known values of d, v sub f, and v sub t in for the factor out in front. After crunching the numbers and multiplying the two fractions together, this brings our infinite sum to 1 hour. So now, finding the total distance that the bird travels, x sub f, is quite trivial. We can substitute 1 hour in for the sum over t sub n, and the bird's velocity of 240 miles per hour in for v sub f, to find the total distance traveled by the bird to be 240 miles. It's great we found the solution, but unless you have a von Neumann level IQ, which sources estimate to be around 190, it's not the most straightforward problem. And what was that trick Max Born was referring to? Well, let's take a step back and visualize this problem in a more graphical way. We have our two trains separated by a distance of 100 miles, and our bird begins at the first train. The bird continues to fly back and forth until the two trains collide at exactly the halfway point of their original separation distance. But notice, while the bird's path is very complicated, the path of the trains is very straightforward. In fact, if we only concentrate on the trains and temporarily ignore the bird, we can easily determine that the trains will collide at the halfway point of 50 miles. And since each train was traveling at 50 miles per hour, we know that the total time of the journey must be 1 hour. Remember, this is what the infinite sum over t sub n converged to. So instead of using the bird's path to determine the time, we could have just determined the total time from the trains alone. And since the bird is traveling at a constant speed, we can just multiply the bird's velocity by 1 hour to determine its total distance, which again is 240 miles. On the surface, this bird and train riddle, famously posed by Max Born and swiftly solved by the brilliant John von Neumann, can appear to be just a lighthearted mental exercise in frivolity. But this riddle really highlights the power of effective problem solving. Pure mathematics certainly reigns king to solving problems, but without proper guidance can lead to unnecessarily complicated solutions. By applying a physics intuition to a seemingly complex system, the problem's irrelevant details fall at the wayside, and the complexity can be drastically reduced. Thought experiments such as these have been and remain one of the key tools used by physicists throughout the centuries. Some notable examples include Maxwell's demon in the second law of thermodynamics, Einstein's train and light beam experiment and relativity, Schrödinger's dead or alive cat and quantum superposition, and Feynman's path integral formulation of quantum mechanics. Some of these thought experiments lead to paradoxes, and even counterintuitive notions of reality. And this is what opens the door for innovation. I hope to cover more of these in future videos, but for now, I'm Dr. John, and thanks for watching. Consider subscribing to my channel and leave me a comment below on your favorite riddle of the mind.